recent years has been a really big influx of machine learning, or the golden age of machine learning. And do you use machine learning today? Do you use it in your day-to-day? Not as a developer or data scientist. Anybody doesn't use machine learning today or thinks they are not using machine learning today in their daily life? Yeah, so no hands. Of course, everybody uses it. It's everywhere. And there are so many products that have machine learning in it now that it's really hard to count. From ad serving to stock exchange to assistants like Alexa and Google, self-driving cars, Gmail type aheads, autonomous analytics, transcription, product recommendation, fraud detection, churn prediction, automatic writing of articles that OpenAI just released, composing music, and the list is going to get longer and longer and longer, and this is not an exhaustive list. So it's everywhere. Products using machine learning are prevalent these days and becoming more and more prevalent as time goes on in all walks of life, both for consumers but also for companies. So the machine learning development process, and data scientists here, I'm sure, know it or do it every day. You are given a problem that you are thinking that you want to solve with machine learning, or you think that it can be solved with machine learning. You define it, you start collecting and preparing the data to run your experiments and see whether it does solve that problem. And then you train and test models, and you iterate back and forth over the collection, the preparation of the data, the training and testing, until you're happy. And there is something that works, that appears to be working accurately enough for it to be useful for the problem it's trying to solve. Now comes the hard part of deploying it into production, so making these models that you train and tested constantly run in production in the environment that they need to run in. And the fifth step is actually making sure that it's still working, tracking and monitoring it. Now, this fifth step is quite overlooked, at least in terms of tooling and the attention that it should get. It's natural because in recent years, really, a lot of the tools and open sources were, and even the deployment processes were centered around just creating these models, just making sure that you get something that is working, that can work and can solve the problem you're trying to solve, whether it's image classification, churn prediction, or fraud detection. While putting it into production, a lot of these projects were still research, and there are a lot of, I can throw here, I didn't want to throw a lot of research from IDC and Gartner that are showing that it's still early stage in many companies applying machine learning. It's still at the stage of this research, but these models are going into production as they're becoming more and more successful. And now comes the hard part of tracking and monitoring it. The problem with tracking and monitoring it, this is not like a normal application. This is not an application where you just have to monitor for errors or server crashing or whether the latency is high. You have to do that for machine learning models as well, but that's not an important part of making sure that it's working. Making sure that it's working means that it should work as well as it did when you train and test, and it depends on the data that you're getting. So as opposed to a lot of applications and monitoring of applications and business processes, these are unique applications that they depend on the data and they're not deterministic. So you have to keep making sure that they're working as you design them. And you can't just throw it on your DevOps people to do it because they wouldn't know what to do. They wouldn't know how to look at it and making sure that it's working. All they can do is make sure that it's running fast enough and that it's running at all. So what can go wrong in production? I mean, there are a few things that can go wrong in production with your models. So I collected some public examples, and I'll give some non-public examples as well. So this is from 2 years ago. South Park trolled Amazon Alexa, Echo, Alexa actually, as the headline says, in the best possible way. Throughout the episode, Cartman kept talking to Alexa. Alexa, do this, Alexa, do that. And anybody who had Alexa in the room, while watching the TV series with the volume high enough, their Alexa would do the same thing. So people reported having shopping carts that look like this with, well, you can read it. So what went wrong here? Actually, the machine learning models worked perfectly. They identified every word perfectly. They identified add to cart. They identified set up your watch. They identified everything, but it's not smart machine learning. It's not smart AI. It doesn't understand the context, and it doesn't understand that this is not something reasonable to add to your cart. So it worked really well, and it got trolled really, really well. This is a more recent example from the end of 2018. Google had a multi-million-dollar oops with their ad software, and they basically took over the internet with this yellow ad for 1 hour because of a glitch in their training software that actually led their bidding algorithms to do bidding at really, really high CPA, or I don't remember the name, $20 for a CPM. And they won all the ad spaces on the internet basically for 1 hour for banner ads of this size. And they ended up paying for it. It cost around $10 million, 1 hour. There are other famous things. So, recently you got in the US saying, a lot of people saying artificial intelligence can be racist. We know it can't be racist. It's not racist, but whatever way you train it, if you have a biased training set, it's going to appear to be racist. Sexist view of women, all sorts of bad press about AI. And this is AI or machine learning working in production. And of course, there are a lot of other smaller problems with a lot of different types of models that you might actually have running in various companies. And there are a lot of things that can go wrong. Let me just give you a few examples before. If you're creating a churn prediction model for your company, whether a telco or a gaming company, and you want to estimate, you want to predict whether a customer might churn on you. It's really important. You train your models with a lot of examples. It's really accurate, and then something goes wrong in the input feature, which causes your churn predictor to make a lot of errors, and you lose money because of that. So you get an increase in churn because your model didn't point you to the people that are really at risk. This is a real example of a campaign in an ad tech company that burned $300,000 of budget in 10 hours because the configuration of the bidding algorithm was misconfigured misconfigured a little, and then $300,000 went out the window in 10 hours for one company. Decrease in purchases for e-commerce because a new version of a recommendation engine had a bug in it. So now it was recommending wrong things, and you see sales going down. Increase in blocked payments. So if you have a fraud detection model that is now it's being fed by a lot of features, and all of a sudden somebody somewhere changed the bank ID in your ETL process, and your ETL flow is not aware of that change, and all of a sudden the input features to your fraud detection model are wrong, and again you block a lot of people, and they make them very unhappy, and they might leave you. So the type of things that can go wrong with machine learning models in production, the most common one that we've seen, problem with the input features. If you have a model that has inputs into it, and there is a whole process of creating those inputs in productions, right? So it's not an experiment you're doing in the lab. This is being computed all the time for all the things it needs to work on. And if there is a problem with that process, you get garbage in, you get garbage out, your models break. Even though they're functioning, your DevOps is not going to notice anything wrong because there are no errors, there's no server crashing, there's no high latency. They're working, they're functioning, but they're not functioning correctly. The example with South Park, so somebody taking advantage of a vulnerability, understanding that they can feed you data that will make the models do something really stupid. Concept appearing, new concept. If you have a classifier now, there is a new concept appearing in the production environment. All of a sudden, that concept might be misclassified and might create really bad results. Concept drift, which happens a lot. So you're training a churn predictor that says what is the probability of a customer of churning, but over time, your profiles of customers changes, and all of a sudden, that model is not accurate anymore, and you have to be aware of it. Otherwise, it's going to, again, be stale and not do the right things. You have problems in training. So if you have a biased training set, when you go to production, all of a sudden you get something completely different. Misclassifications. If you have a problem where you're actually relying on people to classify your examples in production, for some, I mean, some processes this is reasonable. If they give you misclassifications, again, it might screw up your model. So a lot of things can go wrong, and this is the big motivation for actually having monitoring of these machine learning models. Well, how is this different than any other monitoring? So let me give you the framework. So if you're monitoring, you want to monitor whatever your models do and track for unexpected changes. Why unexpected changes? If everything is expected, then you have nothing to do, you have nothing to worry about. But if there's something unexpected that happens, some changes to their behavior that happens over time, that's when you want to be aware of it. So the general framework to do it, first you want to define what are your algorithm's performance metrics. So performance meaning, is it, if I have a classifier and I can get labels even after a little bit when they do the classification in production, probably I want to track my accuracy over time. But there are other things that you might want to define as early indicators that your model might have an issue. Then you want to collect it continuously, and then track it, monitor it somehow to find these unexpected changes. So step one is actually collecting the input and output of the model. So there's the word ML-Watcher here. The reason for it is that we are releasing an open source that is called ML-Watcher that will do this collection for classification models that are written in Python. So I'll describe it in more details a little bit later. So what you want to do for any type of model, whether regression, clustering, but especially classification, you want to track your inputs and you want to track your outputs. And track them in a way, collect what they're doing continuously. So they are continuously getting examples, basically in production. So if I'm doing image classification, they're continuously getting images, new images to classify. They're outputting their classification, what they think is the class, is in the image. So you want to collect that and aggregate statistics about it. What kind of statistics? So as I alluded to, a lot of the problems happen in the inputs, so you want to collect things about the inputs. Because if something breaks in your process creating your input features to your classifier or whatever type of model it is, it's going to create garbage. So you want to look at least at your input feature distribution, things like the means, the STD, the interquartile range, counts, percentiles. If they're discrete, you want to create histograms of it. And you want to track that because it's supposed to be relatively stable over time if you collect and aggregate it over time. The output is probably easier. If it's a classifier, you want to look at the distribution of the predicted classes. If I have a classifier with two classes, and it's usually 50-50 each class, and now all of a sudden I see my classifier predicting 80% for one class and 20% for another class over some window of time, that's probably a good trigger to go look at it, because something might have gone wrong. Maybe it's okay, and maybe the inputs, maybe it's just really the way things happened, but at least you want to be aware of it because it's a strong indication there is a problem. Looking at the confidence of your classifier of the winning class. So if I trained a classifier that usually predicts each class with probability 0.9, and now it's dropping to 0.6, that again may be indicating a problem with my classifier. And if I have labels, and in some cases you can get labels after the fact, you want to look at your accuracy, at your confusion metrics, or whatever statistics you can get out of your confusion metrics. Now you want to track it over time, and then visualize it. So if you're tracking them over time and you're computing these statistics about your models over time, you can put them in dashboards and visualize them, and then when something looks different, you'll notice it and you can now react to it and take care of it. And again, the DevOps people won't know what to do with this drop, so it has to be the data science team that is involved in this process of monitoring. The problem with a dashboard approach that they don't scale. So if you have 5 models in production that you need to take care of, 5 instances of a model or 5 actual models, you can put it on a dashboard and everything's fine. But think about an ad tech company that is running thousands of campaigns, and each campaign has basically an instance of a bidding model that is running that campaign and doing all the bidding. Or if you have a churn prediction model in a large telco company, but you don't have one model because you have lots of cohorts of users. You have the prepaid cards and you have the family plans, and each one would probably have you would have to train probably a different churn prediction model, and all of them are running in parallel in production. Just looking at dashboards would consume all of the data science resources, and there's no real justification for it. At Anodot, we have millions of models running in parallel in production. We cannot visualize all of them to make sure they're all running properly. So the solution is, surprisingly, Anodot is an anomaly detection. We have an anomaly detection service, so that's one of the motivation for the solution, but it is a good solution. Automated anomaly detection at scale. So if you have machine learning algorithms doing anomaly detection, all those time series, all these statistics that you're collecting about your models, then they can alert you whenever something is weird is happening. So that basically frees up your time from looking at dashboards to actually doing your work normally and being alerted only when something strange is happening. So to do this, we've actually built an open source Python ML monitoring agent. So this is unrelated to Anodot. So we happen to write it, and the name of the person who wrote it is Gary Blotin. I'm sorry, it's hidden here. He's an intern. And it's a very simple library that all you have to do is wrap your code that does classification, in this case, with an agent, with a hook, that will start collecting all these statistics. We'll start collecting what the models are doing and then compute the statistics and then report the statistics either to your dashboard, whatever system you collect your time series into, or send it to another system that does anomaly detection. This is an example code. You initialize the agent. It's an agent with a server that does all the aggregations. You can set all sorts of things in it, like the frequency of aggregation. In this case, 1 means 1 minute. What's the buffer size? So if I have a model that does churn prediction, how many samples do I collect before I aggregate it, and so on. So there are all sorts of parameters. And then when you're running your whatever classifier is, it outputs prediction probability. You also know the inputs, and now all you have to do is send those data into that agent that collects it and aggregates it, and then stores it, saves it, sends it to another system. Do whatever you want with it, but at least you have a way to monitor your application. This is kind of the architecture of it. It's an agent. It's a client-server architecture. You might have dozens or hundreds or thousands of algorithms, models running in production. For each one, you put in the hook in the input and the output. You have one server that can collect all of these inputs and outputs for every sample that your model ran on. And then it computes the statistics, basically compresses the data, and stores it. Now, you can store it to JSON files, CSV files, and we also built a hook into the Anodot system that does anomaly detection, and I'm going to demonstrate that as well. So let me demonstrate it with an example of a dummy application, a digit classifier. We took the MNIST image data set. We trained a model for identifying hand digit writing, 0 to 9. So it's a 10-class classification problem. The input images were 28 by 28 pixels. The output is the predicted digit and then the probability of each digit being the right class. So obviously the predicted digit is the maximum of that probability. And so these are the three outputs that we are collecting. The model that we trained, and it's not really important which model it is, we use TensorFlow, neural network with 3 layers, about 200,000 parameters to train. So it's a fairly complex network for this type of problem, but it does really, really well when everything is fine. So just to give you a sense, the expected accuracy is 96 or almost 97% for this problem with that network. And it's also very stable predictions, meaning that whenever it's saying a digit, it's saying it with high probability. So it's both correct and with high probability. So the confidence of the prediction is around, typically around 0.95, which is a very good classifier, especially when it's correct with that prediction. So this is what happens in normal. So when we trained it, this is the expectation of how it should behave. So sometimes something goes wrong with the input, and as I mentioned, this is one of the most common things that happens with these models. The inputs get screwed up for some reason. So can anybody guess what's wrong with the input here? Why is this input wrong?
It's all shifted down.
Yeah, so we basically translated the images a few pixels down. That's all that happened. And this could happen, if you have a sensing system with a camera, it might move a little bit. Now, of course, you can say we can train the model in the first place to be shift invariant. Obviously, you want to do that, so the point of this is not how to do digit recognition and what kind of things to take care of. So, but let's say you didn't train it, or you're using a model that came out from some open system or open AI or open CV that was already trained, but they didn't account for some situations, and all of a sudden your input data is different than the training data. And for us as humans, we still can recognize this very easily. For the models, actually, it does a really, really bad job. If you took that data set, shifted it, and then computed the accuracy, you get 18%, so from 97% to 18%. So the model really doesn't, the model we trained doesn't handle this shift very well. Now, the problem is, if I'm applying this in production, I don't necessarily have the right label. So computing the accuracy in production might not be feasible. So I have to have somebody that tells me you're right or wrong, and in a lot of applications, that's not really available. But are the other measures that I mentioned, can they tell me that something strange is happening with my classifier, even though I don't know that I'm making all these labeling mistakes in production? So basically, yes, and this is the example. So what we did here, we actually continuously ran this doing classification for several hours, about a few images every minute. And then we collected all these measures, both on the output, so the max probability of the classifier and also the input feature distribution. And we let an anomaly detection system, which happens to be ours, learn the normal pattern. What is the normal around all of these? And and we got alerted. So basically, when something strange happened, we got an alert. I have it open here. So the alert in an email looks like this. It basically told me there is an abnormal change in the classifier prediction probability, and there was a 25% drop in the prediction probability. So what happens is the classifiers were both making the wrong decisions, but also their prediction probability was lower. So before it was saying a digit with probability 0.95. Now it's saying 0.7. So it's not as sure of itself as it was. And this is a good time for the data science team to step in and look at that model. And this could be one model out of thousands of models that are in production. Now, when you get this, this might happen and it's natural that it happened and there's nothing wrong. Now you want to investigate it. And that's where the input features come in, because if I see that also something changed in my input features, that's a very good indication that something in my process of collecting the data and creating those features went wrong. So I'm going to spare opening it live, but basically, when you're doing investigation, this is what you're seeing. This is the alert that I got on the max probability distribution. And down here, what you're seeing is there is also a change in the input features because the statistics of every pixel of that image really changed. So I'm going to wrap up in 1 minute. So the key takeaway from this talk, and I'm 37 seconds over time, doing monitoring, whether it's ML-Watcher or some other things, plus automated anomaly detection is really the scalable way to do machine learning monitoring. So when you have 1, 2, 3 models in production, you can get away with just looking at dashboards. When you start deploying massive amounts of models, this doesn't work, it doesn't scale, and you have to have machine learning algorithms monitoring your machine learning algorithms. And in this case, it's anomaly detection. So this is not the right link for the open source. I'm going to publish the right link. If you need the right link, we changed it this morning, and I didn't have time to change it in the presentation. If you need it, just send me an email at ira@anodot.com, and I'll send you the right link. Thank you very much.